Hello guys, you are welcome back to the reaction. In today's lesson, we're going to solve the question on the board using quantum numbers. And the question is as follows. Determine the number of orbitals present when the principal quantum number n is equal to 2. To solve this problem, we need to know the following. We need to know what an orbital is, and we need to know the quantum numbers that describe an orbital. First, an orbital is a region in space where there is a high probability of finding an electron. Also, an orbital is described by 3 quantum numbers: principal quantum number, azimuthal quantum number, and the magnetic quantum number. So, to solve this problem, we need to know the values of the quantum numbers for each of the orbitals present when n is equal to 2. N is equal to 2 means that the principal quantum number is equal to 2. And when you have a given value of n, the values of the azimuthal quantum number ranges from 0 to n minus 1. So what this means is that when n is equal to 2, the values of L will be 0, 2 minus 1. That is, the values of L will be 0 and 1. When we are given the value of the azimuthal quantum number, the values of the magnetic quantum number ranges from minus L to 0 to plus L. So what this means is that when L is equal to 0, that the values of ML, which is the magnetic quantum number, will be minus 0, 0, plus 0, which is equal to 0. So what this means is that when L is equal to 0, the value of Mn is equal to 0. When the value of the azimuthal quantum number, L, is equal to 1, the corresponding values of the magnetic quantum number, Ml, will be minus 1, 0, plus 1. Now, we can specify the quantum numbers that describe each of the orbitals present. When n is equal to 2, the first value of L is 0. N is equal to 0. And when L is equal to 0, the first value of the magnetic quantum number is 0. So ML is 0. The next one, n is equal to 2. When n is equal to 2, the next value of L is 1. So that is n is equal to 1. When n is equal to 1, the first value of ML is minus 1. So ML is equal to minus 1. Also, we have n is equal to 2, n is equal to 1. The next value of ML is 0. So we have ML is equal to 0. And then we have n is equal to 2, n is equal to 1. The last value of ML is plus 1. So in this case, ML is equal to plus 1. To know the orbital that each of these sets of quantum number describes, we need to look at the azimuthal quantum number. The value of the azimuthal quantum number tells us whether an orbital is an s orbital, or a p orbital, or a d orbital, or an f orbital. For the first set, the value of L is 0. So it means that this set of quantum numbers describe an s orbital. Since n is equal to 2, it means that this set of quantum numbers describes a 2s orbital. For the second one, the value of n is equal to 1, and that means the orbital is a p orbital. So this set of quantum numbers describe the 2p orbital. For the next one, L is also equal to 1. So it means that this set of quantum numbers here describe another 2p orbital. For the last set here, L is still equal to 1. So it also means that this set of quantum numbers describe 2p orbital. Now when you look at these three sets of quantum numbers, you will discover that they have the same values of principal quantum number and also the same values of azimuthal quantum number. What this means is that these three orbitals, which have the same values of principal quantum number and azimuthal quantum number, are orbitals that have equal energy. And orbitals that have equal energy are said to be degenerate. So what this means is that the p orbital exhibits degeneracy. So as a result, from here it means that these three 2p orbitals here have equal energy. However, when we look at the set of quantum numbers for these p orbitals, we will discover that the values of their magnetic quantum numbers are different. Let us remember that the magnetic quantum number does not only tell us the number of orbitals in a subshell, it also describes their orientation in space. The fact that these three p orbitals here have different values of magnetic quantum numbers tells you that their orientation in space are different from each other. The first one, which has a magnetic quantum number of -1, is oriented towards the x-axis. The next one, which has a magnetic quantum number of 0, is oriented towards the y-axis. And the final one, which has a magnetic quantum number of +1, is oriented towards the z-axis. So, despite the fact that these three p orbitals have equal energy, their orientations in space are different. So, this means that the 2px orbital in terms of energy is equal to the 2py, and the 2py is equal to what? The 2pz. It is not only the p orbital that exhibits degeneracy. The d orbital also exhibits degeneracy, as well as the f orbital. In the d subshell, there are 5 orbitals that exhibit degeneracy. What this means is that the d orbital is 5-fold degenerate. In the f subshell, there are 7 orbitals that exhibit degeneracy. What this means is that the f orbital is 7-fold degenerate, meaning that there are 7 orbitals in the f subshell that have equal energy. In the d subshell, there are 5 orbitals that have equal energy. In the p subshell, there are 3 orbitals that have equal energy, and they are 2px, 2py, and 2pz. Now, to answer the question, the number of orbitals present when the principal quantum number n is equal to 2 are 1, 2, 3, 4. So therefore, when n is equal to 2, the number of orbitals present is equal to 4. Thank you very much for watching, and see you in the next lesson.